Everyone happy to get started?
Yes, please.
Woohoo! Sweetie, we're off. So this is part 2 of the talk. Anyone here that wasn't here last year? I recognise. Okay, I'll just do a couple of quick roundup. So last year it's all about, in a nutshell, in Delphi, tparallel.4. Okay, that's all I've done. But I'm not going to give you the average Delphi thing here. We're not even going to look at the IDE. There's a few slides of code which come at the end. This is about the problem. Okay? This is about this particular problem. This is a very famous diagram. As I said, it's just the recall. Sorry, that big crap means I can quickly move to the next slide. Sweet. So, last year I talked about the various different algorithms. I've also put, for the people that weren't here for last year, I've put all the slides from last year, expanded a couple and put them in an appendix. So when I give this over to Francesca soon, you'll be able to download that and have a look at it. But basically we looked at it, and there's about 2 to 3 different ways in which we can approach these scheduling problems. So what we're doing here is we're talking about job shop production scheduling, rostering, bin packing, all of those scheduling problems. They're basically the last frontier of unsolved problems in computer science. Okay? And we have a look at them. Now, the normal thing that a Delphi coder is going to do is the first point. Create a search tree. I have, let's go rostering this time. I think last year I did job shop scheduling. Rostering, right? So I've got teams of people. It's an 24-hour ER rostering situation, which, by the way, I have done a couple of decades ago. I attempted a couple of decades ago. So we've got specialised types of staff. We have a mandate on how many people we have. We don't have to worry about the jobs coming in. We just got to schedule people on. Okay? And how would you do it? Search tree. So that's constraint satisfaction programming. I must have a certain number of surgical staff. I must have a certain number of surgical nurses. I need a certain number of registered nurses. And I need some, what do you call the non-nurses? The ward staff. And I need some ward staff, right? And I've got all of these. I've got a HR list coming out of the wazoo. Who do I assign where? And on top of that, HR says, please minimise payroll costs. More than the statutory 34 hours a week. 27 if they're assigned to night shifts at any stage of the week. We have to pay them overtime. So please, while you're at it, minimise it. Finding a schedule is NPC hard. Optimising it for payroll, that's NP hard. That's the typical pattern. It's not the always pattern. The typical pattern is that an NP hard problem is an NPC problem of NPC problems. And that explains the diagram completely to you. But no more on the diagram. Let's get back to coding. We're into Delphi. Okay, so conclusion from last week. And also I mentioned that you might still, as a Delphi programmer, be wowed by randomizing type approaches, typified by genetic algorithms, evolutionary algorithms, etc., ant colony, blah, 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 blah. Whatever the flavor of this year is, it's basically randomizing. And what we looked at is, I showed you an example where me and my guy who's the GPU expert in Nexus, we went through and we created a program that was entirely CSP, and we ran it both using all the cores that we could using tparallel.4, and that's trivial, it's one line of code, provided you set your data structures up right. As a SIMD thing, and spill it over and also do it on the GPU, which brings in more than half an hour's discussion of problems, okay? But I have actually put, for those of you who were here last year, so you might still like to look at the appendix slides, you'll find that I've actually put in a definition of all those things, context memory, what is a kernel, blah, blah, blah. Basically, in CPU land we say this, in GPU land we say this. And be careful of this. So it's not meant to be a test on how to go on the GPU. But if you are going to venture into GPU, have a look at a couple of the definitions, the slides are whacked there, and then go and consult with an LLM. Okay, and so we sort of finished on this problem was what's known as embarrassingly parallelizable. I mean, one line of Fortran code. Parallel dot for brackets, and away you go with the standard parameters. And suddenly, if that works, right, that's what's called embarrassingly parallelizable. And these problems litter the field. Litter the field. For instance, with the example with the ER, what if, to make it SIMD, what are we going to do to make it SIMD the easiest? Somebody, anybody? We've got the list of inputs. What I do, I randomize it. Shake a die, and then put that list, bundle it into the data segment for one thread. And then put a loop over it with a random seed at the top, and suddenly you've got an embarrassingly parallelizable problem. And it will look at different parts of the search space. It's absolutely so easy to do. So is it really? Why is it? Well, here's some of the observations that that you should probably know. So for 50 years, computer scientists have been looking at that diagram. So not specific, on top of all of this research I'm talking about here, right? They've been looking at 50 years. It's an average of about 6,500 academic papers per year on the general problem, still unsolved. It's part of the multi-million-dollar question, which is literally which side of that vertical scale is correct. P is not equal to NP, or P equals NP. Okay? And last year we had a bit of a chat about that, and Delphi can help us deliver a bit of an answer there. So this is something that 50 years research couldn't crack. You know, but it's the problem that makes computer scientists cry. Really? We've solved it. It's embarrassing parallelizable. I'll let you absorb the slide first. It's a joke. The slide. No? Okay. Okay. That, by the way, is not mine. That's my mate found that somewhere in a publication, a conference publication, and it's just too good. Okay? If you are going to do one of these problems, though, if you really do get, or as part of your work, one of these really difficult problems, an NPC or NP hard, worse still, you have to optimize your NPC algorithm implementation. You just go parallel, folks, and Delphi's got everything you want to do. Okay, let's have a bit look at this, right? Because this slide is from last year. I just thought just re-remind you about the challenge of it, why we're doing it. And the 2 points there in the background are what I want to expand upon here, right? Brute force doesn't scale. And so everyone reads that, everyone acknowledges it. And yet I've got someone came up to me in the second half of last year and said, oh, Geoff, can I do a PhD with you in this problem? And I said, sure, Michael, no worries, mate, go for it. And he acknowledged that. And what has he been doing for about 8 months? He's been trying to brute force it. He keeps saying silly things to me like, we'll soon have quantum computers. We've got this, we've got that. And 20 years ago, you couldn't even solve an 8x8. Now we can solve an 8x8. And it's like, Michael, and I should say it's not necessarily him. It's what everyone does and what everyone says when they're first given this problem. Someone comes up to you and someone comes up to you, sir, and says, could you help me schedule my staff at the ER room? It's a consultancy. Why would you say, no, it's impossible? So I'll give it a crack. I'll have a go with it. And the reason you do it is because of these things down. But don't worry about that. That was just a joke to LLMs last year. All right. The experience is literally invaluable. And sometimes we don't want the final solution. We're quite happy with an approximate solution. Approximate solutions means we go down the random path. Okay? So with the example that I've just made up before, the random path, well, the random solution will be this. Grab someone from my list. Is there a vacant, or find a vacant slot, partition my list, use an index, right? Partition my HR list according to the different role types that I have. And in the first slot, what type is it? Randomly select somebody, whack them in, and then go through. Okay? Now that's undoubtedly going to end up with clashes, time clashes if you're not careful. Okay? Where shifts have overlapped, there might be 2 ward shifts. You've randomly selected one person for this shift, and when you did your next random assignment, you actually randomly, if there's 20 people there, there's a 5% chance roughly that you'll randomly select that person again. Okay? So you say, okay, I'll introduce resolutions, etc. Anyway, I think you get the idea. And this is the test case that we used last year. The eternity 2 problem. Why? Fundamentally, apart from all the glitzy bit, there's a $2 million US if you can actually solve this, right? Fundamentally, this is the toughest NPC problem that you'll hit. It's not even NP hard. But as NPC problems go, it's hard. Now, I had a student 20 odd years ago who did a PhD in jigsaw puzzles. This is before this problem came out. And what we found with jigsaw puzzles was that it was trivial. It turns out that these problems scale as n factorial. So in all of these problems, including the one I just gave you, the ER department, right? There's a region where it's just trivial. It's a small country town. They don't operate 24/7 in their ER. They're on call. They've got 2 surgeons, 6 nurses who dub as theatre nurses as well, and 4 wardsmen. And they don't need full coverage. They only need a couple of each type at any one point, except the surgeons don't want one of those, right? It's trivial. So that's what's called the trivial. So if you want to go, get Excel, put any one column, n factorial equals factorial of A1 and drag it down, and then graph that. And you'll see what I'm talking about. You'll end up with a graph that goes like this. So if n is on your x-axis, that's the size of the problem, there is this whole region where it's absolutely trivial, right? And this problem has that region lovely. If I say this is an n by n board, and the actual puzzle, the commercial puzzle, is a 16 by 16 board, nice, 256, we can use Delphi T-sets, that's what I use all the time, and you've got a nice small problem, and that's 256, a 250 piece jigsaw puzzle, that's for kids, right? Why? Why is a human jigsaw puzzle different from this one? Hint, hint, branching factor. Think of it as a tree. Branching factors, somebody, anybody? On a human puzzle, as Thomas has said, you've got a branching factor of 1. There is only one piece that will match to another. You just got to find it because it's got interlocking in it. And what my student did was he even took the interlocking out and said, let's just take an image, and he calculated a function, a metric, it couldn't have a hash function, right, of the pixels up to, off the image, up to 8 pixels deep. And then once you do it, boom, the whole thing falls out. It's just so trivial. Although if it's blue sky on blue sky that you're trying to match, that creates a bit of a problem, but it's still in the trivial regime, right? This is only a 256-piece puzzle, folks. And you cannot solve it. Nobody says, oh, we will go through this. Let's examine this and find out why. So the focus this year, folks, sorry for the long intro to catch up with last year. The focus this year is, okay, well, surely, okay, if this is the hardest of the hardest, if I can solve this, A, I collect $2 million US, B, going back to the diagram that's bothering the computer scientists, there's another $1 million US there to be had, and C, you can collect the Turing Award as well, which is another $1 million. There's $4 million US if you can solve a trivial little, a small 16 by 16 jigsaw puzzle. And $4 million, and fame and fortune, trust me. Actually, you'll make more money, as I think I noted there on another slide from last year, if you don't tell anybody how you did it. You will make, it's multi-trillion-dollar unsolved problem in the world, and global logistics, transport, train transport, just everything relies on this problem. It's been consuming me, not this particular problem, but NPC problems have been consuming me since the early 80s. Oh, I am too old for this. I really should retire. No. And actually, I have from uni. This is my last PhD student, I promise. No more. Blah, blah. Oh, so now, this is new. So those of you who were here last year, this is the start of the brand spanking new stuff, although I did tweak a lot of the previous stuff there. Okay. Dr. G told us in our Delphi Summit presentation to have a first crack random. Okay, screw him. We're going to solve this, make $4 million US, and we're going to solve it via random. Okay. And this is what might be. Oh God, I hope he doesn't. Oh no, this isn't being broadcast, is it? So I've got a chance to edit it before it goes. Sorry, Michael. Yes. Never mind. I didn't say that. Of course, if he did pull out, make life a lot easier for me. So we have 256 pieces. So in our list of personnel to be assigned to the weekly ER schedule roster, right? We have 256 people. Well, randomly put the first one into the first slot. Now, because of the longitudinal nature of rosters and production scheduling and et cetera, and trains spotting and blah, 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 there's an element in here that's not temporal. Like I said, this is the hardest of the easy NPC problems. No temporal aspect, no longitudinal dimension to it. So once we've assigned a piece in, there's only 255 jigsaw pieces, tiles left to put on the board, and we randomly go through. That gives us a number, which is meaningless. There's 4 rotations, but it doesn't matter, because suddenly we think, oh my God! And oddly enough, I haven't actually mentioned this to my student yet. I didn't realise this morning when I was writing the slides, 3 weeks ago when I was writing the slides, well in preparation of this presentation. There are 4, once you put a piece in, it can go in one of 4 positions. But if you look at the puzzle, I don't have it with me, the solution only requires you to put the tile ID in. And then I realised, if you know which tile goes in which position, it's like a human jigsaw puzzle. There is only one. You rotate it until it matches the others and you just build it. It's trivial. It's a polynomial solution. An obvious polynomial solution. Right? So you can actually ignore that. And this reduces to a mere 256, right? Final configuration. So randomly, each time you've rolled the die 255 times, because you have to roll it for the final one, there's only one tile left, right? You've got a 1 in 4.56 by 10 to the 613 chance that it is the solution. Okay? Seems pretty easy. It's a number. Everyone knows numbers. Okay. I'll let you absorb the second joke I put in. Who's read Hitchhiker's Guide to the Galaxy? Who hasn't read Hitchhiker's Guide to the Galaxy? Oh, I recommend it. I actually thought every programmer alive would have been a Douglas Adams fan. Okay. So in that movie, they've got this improbability drive. And if we had one here, the solution pops out, right? And at one point in the book, if someone comes out of the door and goes, oh my God, I've got a room full of monkeys want to talk to me about a script for Hamlet. Remember that bit of the book? Good. I don't want to go on. It's just I always remember. I love it. Anyway, so yes. So what's the analogy on Earth? Oh, everyone needs a villain. So Microsoft, and I was saying this morning, can't be Delphi, C++, right? It can't be the IDE. No worries, Visual Studio. Now we have our villain, and they go, we're going to undercut you. Right? We're going to quote less. And we'll solve it using 20,000 monkeys. And we'll just, tell them work from home, get your own keyboards, away you go, and bang out solutions, right? Now let's suppose, it is only Visual Studio and C++, right? Let's suppose they can generate a complete solution in 1 millisecond, right? And because they're monkeys, they don't need to eat or drink. They've got, can Microsoft provide free coffee? There's one really, really good thing about them, right? No, it's more than one, but it's one of the many advantages working for Microsoft, right? Don't worry, I've never worked there. So I hear. And if we do all of that and we come through, right, that's good except for we're generating this massive number, 16 million solutions a year. Come on, we've got to get across the solution, surely. Surely we're going to solve it if we throw that many resources at it. Well, it doesn't. We know that it doesn't. Okay? So, what do? Well, we go to a Delphi, Microsoft failed. Let's get the Embarcadero Delphi coder. Let's make it fair. Let's put it out to not Embarcadero, but let's put it out to one of us guys, one of the independent Delphi devs. And of course, we're at Microsoft. We don't use Visual Studio. We use a fucking brain, mate. Use a brain. We're going to do it with quantum computers. So it's quantum computers, not quantum computing. Okay, there is a distinction, and that's a totally different talk. I've been working on this for about 8 months now, the quantum computing algorithm for this. And that's a whole new talk, and that needs an hour and a half an hour. Let's assume we've got access in the quantum world, Avogadro's number. I'm a physicist, by the way, by training. Avogadro's number is where we know we're safely in the classical world, in the macro world, I should say, and the number that links us there is Avogadro's number. There's actually a second number, that's Planck's constant, but that's when we want to go to the other side of quantum, and we go to the bottom end of quantum as opposed to the top end. So those are your two most important things, Planck's constant and Avogadro's number. And let's assume that we've got these random quantum oscillators. Think what makes your old non-digital clock work. Remember when they first came out with those pulsing crystals, right? Oscillating crystals. Think of that, right? We've got it here because we have integrity. We're Delphi developers. Excuse me. We have integrity. We've got integrity, mate. Got one of those. And we quote a year to them. Now, what do we so our question is, because we're Delphi developers, we don't go, let's throw 20,000 monkeys. We go, how many monkeys do we need? That's the more smart thing. We're going to do a needs analysis. And we go through, blah, 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 blah. That is, we need 4.44. By the way, I calculated this on the Microsoft calculator, so I hope it's right. Another joke. It's a jockey. He said joke with an E. By 10 to the 537. Okay? Great. We're getting it. Excuse me. Had too many coffees this morning. There's around 10 to the 85 atoms in the universe. If each atom was one of these 5 minutes left, god damn it, 2 years in a row, they'll have to be a part 3 next year. So we go through and we say, well, we need some smarts. Obviously, I missed another joke, Dora. You know, a dumbass random assignment is what this algorithm is, by the way. Dora, you know why it's a joke, don't you? You know with LLMs and the latest training technique, it's LoRa, L-O-R. Come on. How many people here are not yet into LLM coding? No, fine, shoot, never mind. Sorry, apologies, we've got 5 minutes left. And then all the food will be gone. In 5 minutes, you have to run downstairs and get to the end of the line and wait 15 minutes to get lunch. Okay, but, again, another joke. We get Ian. Ian Barker has the answer to everything. So let's get Ian involved. He's a smart dude. And, you know, we're brilliant inside the Henry Pong spot, so yeah, why don't we use, how about we don't use Dora, is what, dumbass random assignment, but still shooting for random, right? Still, we haven't done the lecture with Dr. G yet, so still shooting for random, but this time, let's look at the physical aspects. We know that there are 4 corners, so why randomly choose from those, i.e., there are 4 surgeons. We know that on the borders, there are 56 borders left, like 14 by 4, whenever I multiply by 4, I just double. So 14, 28, 56. So there are 56 edge pieces that are non-corner. Border pieces are edges, not corners. Leaving us 196, but the real puzzle, they fix one piece. And we won't go into the mathematics of what that does to you. And so 195 left to choose. So that's our surgeons, there's our nurses, there's our ward staff. Okay? Literally. Oh, by the way, these problems are all the same mathematically. You solve one, you've solved the rest. The trick is finding the transformation function. So we will never be out of a job as coders. And he gives us a sealed envelope, because he's in, and he says, pay the invoice, you pay the invoice, you open it, and we only need, this time, 10 to the 363 quantum computers. Still not possible. So, actually, I judged it pretty well. This is my final slide. After this, there's like 20 slides, which is about double what I had last year. But what I did was I added, as I said, explanations in. So, what's our takeaway from this, right? And what I haven't written there is when I say we can't brute force it, right? There's not enough. I can't emphasize enough to you how much every single student I've spoken to, and these are students that they've got computer science degrees already, right? Go, yeah, I understand that. And what's the first thing they do? They try to effing brute force it. I don't understand. But what do they, it's just this urge of a coder. It doesn't matter whether it's Pascal, Delphi, whatever, right? Urge of coders to create and implement trees, search trees. They just can't help themselves. I used to be like that. I'd like to think I'm not, of course I still am. Not enough happens. You know why I still am? Because I worry that my students, so if this does go up unedited to the web, Michael, this is your due, I worry that he accidentally stumbles across it. Now, I know it's a 1 in 10 to the 613 chance, and I'm pretty sure my odds are good. I mean, those odds are worse, way worse, than winning in one day every single lotto in America. Okay? Buy one ticket in each of them, or take the one set of numbers and just spur them across all, and you've got a better chance of winning all of them than you have a brute force. But I still worry. It's just the human side. I'm just a nice guy, nice, caring lecturer. We can't outsmart it. Here's analysis. Well, if Ian can't solve it, how can anyone solve it? I love you, Ian. Don't kick me out. And we can't outsource it, right? So again, that overlaps with the first comment, right? But we can parallelize the tree algorithm, which is what I covered, the technical bits that I covered last year, right? If I remember it well, I can't remember too well, but something happened that day. And we can parallelize it, we can use heuristics. Again, this is all in the notes and the appendices, right? Time is up, but never mind, I'm just going to finish this one slide. Thank you very much, Mr. GPU, not GPU man, GDK man. We can use heuristics to heuristics as in don't randomly choose. If one side is already set, don't go for the other 200. Go for the 23 or so that will actually be a fit. They won't cause a conflict. Okay, so it's called conflict resolution. And as per what I showed you last year and is in the code, leverage both your CPU and your GPU. And remember this, the whole reason we're doing this parallelizing research is, and this is what I want to final finish on this, finding good enough solutions in reasonable time is actually not bad for these problems. In terms of the city-sized ER department and schedule, right? So they've got to pay somebody 7 hours of overtime. Nah. It's better than not having a schedule at all, right? And at the very end, let the business sort it out. Give them something that generates, but never say you've got, please, if the one thing about everything else is when you're in one of these problems, never ever tell anybody, ever say, I've solved it for you. Right? You haven't. You may have solved something in the trivial region because of the constraints they put on. I only want you to schedule my nurses. Don't worry about the wardsmen, because that's the majority. Just do the nurses. Don't worry about the 2 surgeons, because I can do that myself. They've got contracts. Just do the nursing stuff. Right? Don't say, I've got the solution for you. Don't, please. Say, I can give you reasonable schedules, and you just need to nut out the final details. You know, there might be a 1 in 100 chance, you know, say something like that. If you want to confuse it with problem stats, by all means, all right? So it's that last bit here, right? So yeah, it's not about solving it perfectly to me, right? And this is probably for me what I like about Delphi, the professional Delphi developers I've met over the many decades, Delphi and Pascal, Pascal, blah, 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 right? Is that I find Delphi developers really are grounded in they are definitely in the realism bubble, right? They don't say, oh, Microsoft will solve it for me next year, right? Something like, again, I'm not trying to kick Microsoft, I'm just sort of pointing out what happens. And it's not about solving it perfectly, it's about getting a practical solution for your client, okay? It's embarrassingly trivial. Have I finished on another joke? It's a jockey, folks. J-O-K-E, jockey. Yeah, right. I went one jockey too many, eh? Hey, folks, well, thank you for that. I really wished I'd had an hour, but apparently I was slotted half an hour. So, part 3 next year, and we'll move on to literally this bit here. Okay? I hope I've convinced everybody that random is your good first deliverable. There's nothing wrong with doing actually, a lot of this is why I'm emphasising it, because so few people will do random. Do random. It establishes it's your benchmark. You can't do worse than random. With random, you are going to generate solutions. They're just going to be horribly expensive. Okay? But you will generate solutions. How long does it take to set up a list of slots, a list of names or objects to be packed into bins, whatever, trains to be scheduled on the rail, on the tracks, right? How long does it take to randomly run a loop over it and assign 1 to 1? Doesn't take any time at all. And that, the people that start that way, normally go down evolutionary algorithm paths, right? I don't want you to do that. I want you to use that because of the random path. You've got the big numbers working against you, right? These randomizing evolutionary algorithms and genetic algorithms, they are very good at getting very close to optimal solutions, and because it's randomizing, really quickly. Tree traversal algorithm. They will. It's embarrassing. I gave up trying to beat them to the first solution, right, because of constraint propagation, blah, 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 blah. Go and read a book on it. We don't have time. But yeah, but establish random. As I said, I'll reinforce. You've got a deliverable, and you can't do any worse than that. You literally can't, okay? Because it's random. Then implement your tree traversal and try and make it generate more valuable solutions than the random assignment. I think it's all been turned off. I don't even think we've got time for a Q&A if you want to go and join the line for lunch, folks. But I'm happy for the odd quick question. No?
I have one. You forgot to put a limit on your universe.
Oh, yeah!
Simple one, visible one, reachable one, because there are multiple limits.
Yes, there are.
So then you have a different number of atoms, depending on...
Yeah, it depends on... Well, actually, so what we could have done was said every subatomic particle. We could go even smaller, every quark. Right? We could solve the CP... violation dilemma of the early universe, and let them all live forever. You know, the antimatter as well as the matter. Yes, if you look at it from a physics perspective. Yeah, sorry.
How many solutions are known so far, and how many do we...
0. Oh, sorry, 1. Apologies. It's in a safe. It's in a safe somewhere. There is one because there's what's called the creator's solution. Also commonly called God's solution, right? But if you create the puzzle, right, and that's the first thing you'll do if you try and look at this puzzle, is you'll write an algorithm that generates smaller puzzles for you, right?
You did that last year. I think you showed it being computed on the GPU.
Oh, yes, that's right. Last year I did too. Sorry. Thomas, you are correct. Yes, I showed you. You can easily create these problems, right? And they can be solved in polynomial time. In fact, linear, because you know, tile 18 is in the first position. Tile 23 is in the second position because you created it, right? But if you lose a slip of paper where you wrote down the order of the tiles after you cut it up, you're back to this. Okay? You are back to this, baby. And I assure you, it's not pretty. It's way too long. Any of the quickies before? The line must be getting smaller now. Lunch is beckoning. The coffee is calling. No. Okay. Look, I did it without. Can't believe it's a dry conference. Can you believe that? There's no alcohol. Last year, I was able to get pissed as a newt before I did this. I'm so glad they're no longer recording this. Okay, folks.